That was more general. Sorry, pausing again. So if you want to think of it, descriptive statistics is about describing whether your sample really worked. Right? So it's basically, if you want to think of it, descriptive statistics is all about alerting you to any wonkiness in your data. Right? That's really what you use it for. So it's not going to tell you much about the questions you're interested in. So volunteer, somebody who's doing a quantitative study. Yeah, so what are your two variables?
Gun laws or I should say the strictness of gun laws and the population of an urban city.
So strictness of gun laws and population of urban cities, right? So those are his two variables, right? Descriptive statistics will never be able to tell you if there's a relationship between those two things, right? Even if you create all the multivariate tables you want and look at all the percentages, it'll never tell you that. But what it will tell you is, what does your sample look like? Are you getting enough examples of places with strict gun laws to make assumptions about on the other end when you do your statistics, right? So that's really what descriptive statistics are about, is it's sort of like informing you about your data. So we're going to look at a few, we're going to look at some of the basics of statistics, or go through some of the basics of statistics for those of you who haven't had it before. And for those of you who had, this will be just sort of a nice refresher. Also, descriptive statistics are sometimes referred to as all these chalkboards on the other side here. There's no chalk. Are sometimes also referred to as univariate analysis. So sometimes some descriptives are analyzing one variable at a time, they're univariate analysis. These are particularly true of our measures of central tendency, right? So the measures of central tendency and our measures of dispersion, and we'll look at what those are. Okay, does anybody know of measures of central tendency, what this term means from your stats class? What would be an example of a measure of central tendency? We're going back over this. Oh, go ahead.
What is I don't know if it is, but the 68, 90, 95 rule or whatever?
Well, that's going to be your, that's going to be standard deviation, and that's going to be a measure of dispersion. So measures of central tendency just tells you, basically it gives you a mark of what the center of your sample is on a given variable, right? So what the center of your sample is on a given variable. So let's say the most commonly used measure of central tendency is your mean. Right? Does anybody know what a mean is in everyday parlance? What's the word that we use?
Average.
Average. So when we talk about average, right, that's the measure of central tendency of the mean. So let's calculate that real quick. Average. So your guys' average age is 20.57 years of age, and your average number of pets is 2.07. Right? Does anybody know how you calculate an average? Does anybody remember this from statistics?
You add all the numbers together and then you divide them by how many answers there are, or people there are.
Yeah, so you would take this, right? You would essentially add up all the cases. The way they do it in Excel is all the people who reported. So all these blank ones are just factored out, right? They're just dropped from the case. And then what it does is it divides out by the number of cases, right? So totals and then divides, right? So they may know a problem with averages.
Numbers can be skewed, or inference can be skewed in general average.
Yeah, so averages are particularly prone to something called outliers, right? Outliers are extreme cases. So if we were to take this example, our fictitious person, let's say he is 97 years of age. In some states they have where if you are an elderly person, you can take classes for free in colleges. So they can just take classes for free. When I was teaching in Tennessee, that's the rule in Tennessee. So if it's a state institution, if you're over the age of 65, your classes are completely free. Which means that you get people in your classes that are retired people who just like are there for fun, right? And so like if you think about it, like your average age in class would be pretty extreme. So this makes for some like awkward moments, especially like I had one elderly woman who had Tourette syndrome, and she would just like start saying really random things in class, and people would get really uncomfortable, like sexual things, just really strange stuff. Anyways, let's not get rid of that. Okay, so let's total up this average now with. So how is it? That didn't work.
Yeah, then it already factored it in.
Oh, and I typed it in. Oh, thank you. So, yeah, that leaps our medium age up to something a lot higher, right? Does anybody know how you will figure out if you have outliers? Because if you're talking about, like, it's one thing when we have, 28 cases. Does anybody know what you're going to use to figure that out? You're going to figure that out through your standard deviation. Your standard deviation will tell you how tight things are around that mean, right? So if you have a really wide standard deviation, it's probably not wise to use an average as a measure of central tendency. This will have, and we're not going to get into like more complicated statistics in this class, but that does, like, there is ramifications on which statistical test you use and how you would analyze the data differently at the next level, the level of regression, depending on what happens in your descriptive statistics, as well as how big your sample is, things like that as well, and the type of data you generated. Okay. So, we could do this very easily. Let's say he has 25 paths, right? And the same thing would happen, right? We would all of a sudden have so that would leap our average number of pets up to 1.6. Does anybody know a variable you never want to use averages for, or anything that means that you have a good central tendency? Income, right? Because if you get somebody in your sample, like, the average income, like if we were to take average parents' income, right, from the group in this room, it would probably be a pretty good sample. But if Bill Gates' kids walked in, all of a sudden our average would probably be like 3 million. Right? So like, that's something that you have to be really sensitive about with certain variables. Okay, so that's how you conduct, does anybody know any other than means, right? Means or averages, which are just two words for the same thing. For some reason, mathematicians decided to call an average something different at some point. Does anybody know any other measures of central tendency? So if this one's bad in certain circumstances, what do you do? What are some others?
Median.
The median. Does anybody know how you create a median? So a median would be your middle case. So if we were to right there. Sort, custom sort, sort by age. Okay. So literally what you're doing for your median is you go one case above, one case below, right? So in this case we're not, so if you were to 20, 23, 22, right? And which one ends up being our median? It's going to end up being 20, right? So basically that's all a median is you line, if you were in, you do an equation for it, but in essence what it would be is if you were to line things up, right? Whatever would fall in the middlemost point would be a median. Does anyone see why that overcomes the difficulty of averages? Because what would happen if we had one case that was really high? Let's say, we had a 97-year-old in our sample again. What would happen to that person?
It would be the number in the middle, so it would go down.
Yeah, and most of the time it's going to have literally no effect, right? The reason why means are so important still is you can do things mathematically with them that you can't do with the others, right? But in some ways the median and the last one is modal will give you a better understanding, right, of what is your central tendency. So, okay, modal. Does the people know what the modal score is? What's your modal score?
Most common.
Most common, right? So, your most common is obviously which? Most of you guys are how old? 20, right? Okay. So what that's measuring, if you're thinking about so really all that we're measuring with these numbers is we are measuring, if we were to take our samples and plot them, we are just looking for what is that central most point. Right? Which in a lot of ways means and it means very much so the same thing as how do we use the word average in everyday life? Like not the mathematical use of the word, but like how we just use it.
What's the most common?
Yeah, we mean average is just common, right? And then we really like if we're talking about within the distribution, right, within the bell curve, this is the most common. And people are aware of what the bell curve is, right? So the bell curve is essentially usually on any given measure, you're going to have a high peak in the center and then smaller numbers of cases on the outside. Where you really get difficulties in central tendency is when you get skewed. So I said income is a great example. So what you get, how poor can you get? Quite literally. What's the poorest a person can get?
No money.
Nothing, yeah, 0. Doesn't get much poorer. So let's, for a second, see. Let's ask average U.S. $63,000. 63,000 $. Okay, let's see what our.
That is the median though.
Median U.S. income. Oh, that was median. I said it's average. Now, nobody seems to, everyone knows you're not supposed to measure it that way, apparently. Mean U.S. income. The mean U.S. income is $72,000. How rich can a person get? Let's see what the richest person is in the United States. $3.2 trillion. So if we were to draw that, unfortunately I made my marks way too far this way. So we have 3.2 trillion.
That's 400 people.
Was that?
That's 400.
That was, I was just. Okay, 145 billion. Right, isn't that what it says?
Yeah.
145 billion. I was reading quick. Okay, so $145 billion. So our central tendency, where are they closer to?
0.
They're closer to 0, right? So what you get in is your Bell distribution probably looks a little like, this. And it would just trail on for quite a while, right? So that's how exactly why income becomes a bad measure, is essentially it's being caught, everything will be constantly skewed, right, in the other direction. Just to kind of illustrate. Okay. Next is our measure of dispersion. There are 2 measures of dispersion that are really important. So one is range, right? And what is our range? What does our sample up here range from? If we were to sample everyone in the United States, what's the range?
145 billion.
Yeah, there's a range of 145 million, right? From 0 to 100. What would be the range of our number of pets?
Including Wally.
Let's exclude Wally, since he's not real. I'm not for excluding people.
So it's 0 to 4.
Was that?
Would it be 4?
Yeah, 0 to 4, it'd be 4, right? Sometimes range in studies like on graphs will actually be, rather than represented as like one number like you learn in descriptive statistics, sometimes they will also give the range of 0 to 145 billion or 0 to 4, right? Just so we're on it, on the topic, when you see n on a graph, what is n? You know this? What n stands for?
Wouldn't that be the number of samples that were collected?
It's the what?
The number of samples that are collected?
Yeah, it's the number of cases. Every graph will include the number of cases. And I probably said this, it varies a little depending on which test you use, but if you have less than 1,000 cases in your N, it probably means that whatever statistics you're looking at are invalid, right? That they don't actually meet the requirements of the statistics test. With that said, in some disciplines they do it all the time. A good example of the psychology will regularly run statistics on data of under 30 people, which is kind of mathematically not really, it's kind of meaningless, but people still do it all the time. We'll look at some other examples of ways in which people break it in our own discipline when we get into the elaboration method. Okay. So the other measure of dispersion, what measures of dispersion really capture is they just kind of capture how much, right, the data that we have fans out from that central tendency. Right? So range is one way that we do that. What's another way? And somebody already brought up this number once. What's another way that we measure, right, central tendencies?
Standard deviation. Standard deviation.
Yeah, standard deviation. Right, so standard deviation is basically when you have a good even bell curve, something that never exists in reality. Statistics is totally based off of a unicorn that's not real. It's totally true, the bell curve, no one has a good distribution. It's never really happened. I don't think there exists one in nature. I think it's just an abstract concept that people came up with. So let's say, nonetheless, we'll say we have a nice even bell curve, right? So basically, and somebody referred to this, and this was in our book. So standard deviations. So this is one standard deviation. This is two standard deviation. What number of cases fall between the mean and the first standard deviation? Anyone? I heard somebody say this before. That was you, wasn't it?
68%.
68%, yes. 68% of cases.
Wouldn't that be for both
Yeah,
sides?
isn't that both sides?
It is. I'm just drawing it this way. Yeah, it's for both sides. And then, what percentage of cases fall between the median and the second standard deviation?
95.
95%. Yeah. So does anybody know what happens to your distribution as your standard deviation goes up versus down? What does a low standard deviation mean?
That a lot of cases are near the mean.
Yeah, that a lot of cases are near the measure of central tendency, right? So that means that the lower your standard deviation, the higher your peak, right? Which means that if you have a high standard deviation, what's going to happen? Yeah, it's going to flatten out. So, okay, I said that you use your standard deviation to determine whether you're going to use an average. Why do you think that might be? Anyone want to guess? What's going to happen if you have outliers? So if rather than a nice even distribution, your distribution looks like this, what's going to happen to your standard deviation? What do you think? It's going to increase. right? So outliers increase your standard deviation. So if you have a really high standard deviation, it often means that you have a sample that's positively or negatively skewed. In reality, that's what it usually means. There are cases where you'll have sort of like real shallow distributions, but usually if you have a large enough sample size, that's not going to be the case. So if you have a very small sample size, your standard deviation often increases as well. So let's look at, quickly, so our standard deviation is 0.93, which means that in this room, what does our age distribution look like? What do you think? Is it a high or a low standard deviation score? Yeah, it's a low standard deviation score. It's under 1, right? So but basically we have this kind of distribution around our mean. Almost everybody is within a couple of years of each other. So if we were to then throw, something else in there, what happened to our standard deviation? If my grandfather walked into this room, or really, even if you probably added me into this room, it probably would skyrocket as well. But it jumped from under 1 standard deviation to 19. Right? Let's see what happens from here. Made poor Jack really well. So let's do me. Right there, that's still really skewed, right? Your data. So now we're at 4.5 standard deviations rather than under 1. So, and you could literally, and so that would cause a distribution right there that looks a lot like this, right? Which means that you have outliers skewing your data. What does that mean when it comes to, well, actually, I'll pause on that for a second. So let's move, so that's univariate analysis. We're looking at one variable at a time, right? So bivariate analysis, what you're going to do is, this is when you start comparing. So let's resort our data again. Custom sort. Let's sort by class standing. So what's the number of cases we have of juniors in this class according to grading zone? I know it's false. If people want, I can correct theirs to make it correct. We have 15 cases of seniors, so if we were to do class standing, the age, and this is how you would just construct a bivariate table, right? So Well, let's not do age. Let's do it by number of pets. So we have 0, 1, 2, 3, 4. Yep. 0, 1, 2, 3, 4. Then we have freshman, sophomore, junior, senior. So how many juniors with 2 pets do we have? People read that well enough to read? 4. 1. We have 2 juniors with, oh, 3. We have 3 juniors with 2 pets. So our juniors with 2 pets, we have 3. Okay. How many juniors do we have with 1 pet? What's that?
2.
We have 3.
It's on the top of the board.
How many juniors with 4 pets? 2. How many juniors with no pets? 1. How many juniors with 3 pets? So the only thing you can usually, so sometimes you'll see bivariate tables included. It's pretty rare. It's usually only if it's specifically significant that something is kind of in the way about it. Like there's something wonky with it. It's not a lot of information you can get out of doing bivariate tables like this, right? In essence, like the only information, same with the multivariate tables, which the author shows, that are just more complicated versions of this, right? Where you have more variables in play. The only thing that you're getting really is the percentage of cases that fall into different categories, or literally sometimes just the number of cases that would fall into different categories. So we might visually be able to be like, well, it seems like something's happening, but that's not particularly scientific. So it's very rare that you'll get people doing that. Does anybody know what most bivariate or multivariate analysis is done in statistics? If you had to take other classes with me, you probably had to look at a lot of tables like this. Does anybody know what kind of statistical test you do? So most bivariate, well actually nobody ever does bivariate analysis, but yeah, it died. Okay. So generally speaking, what you're going to use for anything that's usually referred to as statistics is going to be correlation or regression. Regression is going to be the most important. So I would say 90% of the time, if you're looking at a statistical study, it's doing a regression analysis, right? Has anyone ever seen a regression table before? So we'll look at some of these later because I'm going to give us examples of how you would write up your results towards the end. We're going to have several different, particularly well-written articles from different methods that we've looked at. And we have 2 qualitative and 2 quantitative articles. But just as a quick explanation, usually what you'll get is you'll get whatever variable you're interested in at the top, right? So traditionally this would be your independent variable, but nowadays it seems like people kind of go both ways on it. You guys know the difference between independent variable and dependent variable. We talked about this before. Just as a review, what are the difference? Differences. What's the difference between an independent variable and a dependent variable? What's an independent variable? Independent variables, right, are the cause. Right? Dependent variable is the one thing that's changed. Right? That's usually how it explains. Most of the time, how do we know whether one's an independent, whether the variable is independent or dependent? We don't. Right? It's just a logical inference that we make. There is one rule of thumb that something cannot be a dependent variable. Something that predates the other variable cannot be dependent. So it can't be an effect. I gave you guys the example before of like, a lot of times people will talk about things like hard work causes people's poverty. It's an illogical statement, right? Because most people in the United States who are poor are born poor. So their poverty predates, right? So you could make a distinction. I don't think this is probably true, but if you were to measure hard work, it would be like people who, are poor don't work as much, right? I think that's possibly true because of underemployment, right? But like, you can't make the claim that they got poor by not working because being poor predated anything they did in terms of work, right? So that's the one rule that logically you can follow. Whatever comes first has to be the independent variable. But other than that, it's all kind of interpretation of the data. You're interpreting it as being independent. So so you have your variable on top. Like I said, traditionally your independent variable. So if we were to, try to make some sort of inference, whether class standing maybe has anything to do with, whether age has anything to do with class standing, right? You would have age. Of course, you would have to collapse the variable of age into categories to put it onto a table, right? So you'd have to collapse that data into categories. Maybe not in our analysis so much. We have 20, 21, 23, so we could do 20, 20, right, 21, and let's just do 22 greater than 21. That could be our categories, right? From there, essentially what you do is you have your different dependent variables. So does your age determine your class standing? Well, probably, right? So what you report is you report whatever numbers were in the category. And these are meaningless when you look at a statistical chart. So the numbers themselves don't mean anything. The important thing is there a negative or not? And then, is there stars? Right? Yeah.
How would you get a negative number?
So a negative, correlations and regressions can be negative. I was just about to explain that. So it can be negative or it can be positive. A positive relationship means that as one thing goes up, the other goes up. Right? A negative relationship means as one goes up, the other goes down. So which kind of relationship would you have, do you think, in a relationship between your age and how far along you are in college? Yeah, it'd be a positive relationship. If your age goes up, the probability that you're higher along in college would probably go up. And that's despite the fact that we would obviously, in a distribution, have outliers. Right? Non-traditionals becoming more outliers every year. When I was in school, about 10% of your class was usually non-traditionals. I kind of missed that. You know, like I haven't taught in a classroom where, you know, you have a 30-year-old fish roadie who decided all of a sudden they wanted to go get a degree, which is great, and I kind of missed that. But anyways, going back to, so class standing, right, you have, sorry, there's going to be probably a positive. There is something to the number of stars on a graph, and this is all agreed upon. Stars represent p-values. Has anyone ever heard of a p-value before? So p-values are the probability. I know, the poor people in racing up this year, like we just did this with a graph this week. So p-values are the probability that the relationship between the two is random. Right? So the probability that the numbers, that people's age and the number they have, or what they got assigned for their class standing, right, is random. Which it obviously isn't, right? But there would be the probability that that is true. And in essence, as p-values go up, the number of stars will go up. So anytime you see a star, it's a significant, statistically significant relationship. Anytime you see stars, it's a statistically significant relationship. The more stars you get, it's not, and people will talk this way, people will be like, it's a stronger relationship. That's not actually true. You'll see authors write this all the time even. It's not true. As the p-value goes up, it doesn't mean that the relationship is stronger. It just means that the probability it is just random is gone down, right? So if you had 2 stars, it would mean we can be that much more confident that on this line, right, that that people being 20 and their class standing being whatever is related, right? That's how that would work. And then usually these statistical charts will have a bunch of variables. So there'll be like 10, 15 variables, some of which will have relationships, some of which won't. And then usually all they'll do is they'll report back and they'll try to interpret why they got the numbers they did, right? Why these numbers exist the way that they do. Make sense so far? Okay, cool. So that's how you, so is that, everyone clear on this idea of regression, studying the relationship between things? How this works? Going back to like if you're in statistics, this is probably not. And then if you're in my classes, you probably get this a little bit in repetition. But I think it's hard to hold on to otherwise. And then, like I said, we'll look at some actual statistical charts later. So I'm going to hold off there. And from there, what we're going to talk about is we're going to talk about the elaboration model, which is going to get us from having relationships to understanding how to interpret them. So the elaboration model is the kind of rules that you follow to understand what these correlations mean. Going back to like, still at this point, even saying that you have statistically significant relationships is meaningless unless you interpret them, right? So we'll talk about how people go about, or at least one way people go about interpreting, as well as some of the traps, very common traps that people fall into that are technically pseudoscience when you're doing them, but are maybe even as common as doing it the right way. So, as depressing as that is. Any questions or thoughts? Wow. Great, cool. Tuesday we will continue talking about how to interpret statistical data. In your guys's